James Webb just spotted a world where the clouds themselves are made of vaporized rock. It's called WASP 121b, a gas giant 880 light-years away, so hot its dayside boils past 3,000 degrees Celsius. Iron and magnesium rise as gas, drift toward the frozen night, then condense into mineral clouds. On this locked world, it may actually rain molten metal and silicate stone. But how does anything survive being cooked and frozen at the same time? That question is where our story begins, because WASP 121b is a planet that, by the logic of our own solar system, should not exist. It sits roughly 880 light-years from Earth in the southern constellation of Puppis. Wrapped tight around a bright star is a giant so close to its sun that it seems to defy the rules. Webb turned its instruments toward it precisely because it breaks those rules so completely. Astronomers using the WASP survey caught it in 2015, a hunt built to notice tiny dips in starlight when a planet passes in front of its sun. The discovery paper, led by Leslie Hebb and a team drawing on the WASP South telescopes in Sutherland, South Africa, cataloged the object formally as WASP 121b, orbiting a star slightly larger and hotter than our sun, about 1.4 times its mass and burning near 6,460 Kelvin. WASP 121b announced itself with a dip that came again and again, far too often. This planet does not take a lazy year to circle its star. It completes an entire orbit in just 30 hours. To be precise, one loop takes only 1.27 days, and the planet sits a mere 3.8 million kilometers from its star, roughly 1/40th the distance between Earth and our sun. 30 hours to loop a star is a velocity that borders on violence. Imagine a whole year compressed into a day and a half. That closeness is the single fact from which everything strange about this planet flows, and it sets up a punishment that never lets go of the surface below. The giant itself is inflated by that nearness, swollen to roughly 1.9 times the width of Jupiter while holding only about 1.18 times its mass, giving it a puffed up, low-density body that its star pulls at without mercy. That punishment comes from tidal locking. WASP 121b is so near its star, the gravitational tug so relentless, that the planet no longer spins freely against its sun. One face is pinned toward the light for all time. The other is turned forever away, staring into the dark. There is no sunrise here and no sunset. There is only day and only night, frozen into two permanent halves of a single world. That same tidal grip is slowly distorting the planet into a football shape, stretching it along the line that connects it to the star, a deformation astronomers have actually measured in its passing shadow. On the half held in permanent day, the numbers stop sounding like weather and start sounding like a furnace. The dayside climbs past 3,000 degrees Celsius, with measurements from the Hubble Space Telescope in 2019 pegging the hottest regions near 2,500 to 3,000 Kelvin. This places WASP 121b in a rare category astronomers call an ultra-hot Jupiter, a class defined by dayside temperatures above roughly 2,200 Kelvin, of which only a few dozen are known. It is a gas giant, larger than the planet it is named after, but bathed in a heat so extreme that ordinary chemistry begins to come apart. When chemistry comes apart at those temperatures, the very idea of solid ground dissolves. On Earth, rock is the definition of permanence. But heat this savage does not respect stone. Push a mineral past 3,000 degrees and it lets go of itself entirely and lifts into the air as vapor. On WASP 121b, the rock does not stay rock. It becomes sky. That transformation is not a guess. Webb and earlier instruments detected iron and magnesium in the planet's atmosphere, drifting as free gas across the blazing dayside. A 2017 study using Hubble found the first clear signs of glowing water high in the atmosphere, and in 2020, a team led by Thomas McCall Evans and later Jens Hohmakers used ESO's Very Large Telescope in Chile to identify a full pharmacy of vaporized metals: iron, magnesium, chromium, vanadium, calcium, sodium, nickel, and more, all detected as free atoms streaming through the air. These are metals we associate with anvils and mountain cores, and here they float. Alongside them ride silicate materials, the same compounds that make up ordinary rock, now vaporized into the raw ingredients of clouds, a world's minerals hanging in its air. With those ingredients suspended in the atmosphere, the next question is how they move. Heat does not sit politely on the day side. It fights to escape, and on a planet split into scorching day and frozen night, that fight becomes a storm of unimaginable scale. Webb's job was to trace that flow, to watch how the fire on one side reaches toward the ice on the other. In 2025, an international team led by Thomas McCall Evans published a Webb study that mapped the atmosphere across 3 dimensions for the first time, using the telescope's NIRSPEC instrument to slice the planet into vertical layers as it crossed the face of its star. To trace it, Webb works in infrared light, the language of heat itself. Where our eyes see nothing, the telescope reads warmth, mapping which parts of the atmosphere burn and which begin to cool. And what it maps is a planet driven by winds that shame every storm we know. On ultra-hot Jupiters like this one, winds can scream past 18,000 kilometers an hour, dragging heat from the day side and hurling it toward the darkness beyond. On WASP 121b specifically, the Webb data traced a deep jet stream of gas racing eastward at speeds near 5 kilometers a second, roughly 7 times faster than the strongest winds ever recorded on Earth. That heat does not survive the journey unchanged. The night side of WASP 121b is dramatically cooler than the face that stares into the star, dropping to somewhere near 1,500 Kelvin, a difference of more than 1,000 degrees between the two halves of a single world. As the vaporized rock is carried into that cold, what rose as gas can no longer hold its form. The mineral vapor begins to condense, gathering into fine particles until the night sky fills with clouds made of stone. Clouds made of stone are only the beginning, because this temperature gradient does more than form them. The enormous difference between the searing day and the frigid night acts like an engine, driving chemistry in one direction on one side and reversing it on the other. Materials that exist as gas in the light become solid grains in the dark. It is a planet-wide sorting machine, powered by nothing but the gap between fire and ice. Astronomers modeling this cycle predict that clouds of corundum, the same aluminum oxide mineral that forms rubies and sapphires on Earth, could condense in the cooler upper reaches, seeding the night with gem-like grains. And where there are clouds and cooling, there can be rain, though not the rain any of us have felt. In the cooler regions of WASP 121b, the condensed minerals may gather into droplets and fall. Picture it: liquid iron, molten rock, silicate stone forming into drops and drifting down through a metal-laced sky. This is precipitation in the truest sense, but its cycle has nothing to do with water. And yet the physics is oddly familiar. Just as water evaporates from our oceans, rises, cools, and returns as rain, here rock evaporates from the blazing day, rides the winds into the dark, cools, and falls. Swap water for iron, and the planet runs a storm system built entirely from the materials of the ground. It rains what the surface is made of. The Webb team found direct evidence of this circulation. Iron vapor concentrated near the hot day side, and titanium-bearing gas appearing at a different altitude, a chemical layering that only a moving, sorting atmosphere could produce. For all that molten violence, one detail feels almost tender. In the middle of this inferno, Webb found water. Signatures of water vapor appear in the light that filters through the planet's atmosphere, captured in what scientists call transmission spectra, the fingerprint left when starlight passes through gas. Something as delicate as a water molecule endures here, in a place that boils metal. That endurance is not simple survival. On the scalding day side, the heat is so intense that water molecules are torn apart, their atoms ripped from one another. But as those atoms sweep toward the cooler night, they find each other again and reform. Water is destroyed and reborn on a loop that wraps the entire planet. Webb reads this cycle through infrared spectroscopy, decoding the atmosphere's chemistry from patterns in light too faint for any human eye. The same 2025 observations detected carbon monoxide alongside the water, another molecule whose survival and distribution helps astronomers reconstruct exactly how gas flows between the burning and frozen faces. Reading that chemistry revealed something else, something that hints at the planet's fate. The heat is so extreme that the upper atmosphere does not stay put. It swells outward, bloated by energy, until it begins to bleed away into space. WASP-121b is not simply enduring its star. It is being consumed by it, one thin layer at a time. That slow consumption carries the planet's own metals with it. Heavy elements, iron and magnesium and their kin, are lifted into an extended envelope that streams off the planet like a tail. The star strips this material away steadily, pulling the giant apart across timescales we can barely fathom. Hubble observations in 2019 found magnesium and iron escaping the planet's gravity entirely, the first time such heavy metals had been seen fleeing an exoplanet, and the star itself is expected to swallow WASP-121b completely within a few 100 million years as its orbit slowly decays. WASP-121b is living inside its own destruction, glowing brilliantly as it loses itself. Yet to call this world a simple furnace losing mass would miss what Webb revealed. The telescope did not find a static ball of fire. It found a planet with depth, with layers, with weather that changes as you move through the atmosphere. Different altitudes showed different chemistry, as though the planet were built from stacked worlds, each with its own recipe of gas and grain and metal. Those stacked layers are stirred by machinery that never rests. Winds and jets tear across the planet, redistributing heat in ways that shift and evolve rather than settle. The data does not show a single steady state. It shows a climate, restless and three-dimensional, churning between its extremes. WASP-121b is not a frozen portrait of hell. It is a living storm, caught mid-motion. A living storm, this alien turns the planet into something priceless to science. WASP-121b has become a natural laboratory, running experiments no facility on Earth could contain. We cannot vaporize rock into clouds and watch it rain metal in any lab we could build. But here it happens on a planetary scale, freely offered to any telescope patient enough to look. By looking, we test ideas we could never test at home. The conditions on WASP-121b push our models of extreme planetary atmospheres to their breaking point, showing us which theories survive contact with reality and which collapse. For the first time, astronomers are watching rock vapor chemistry unfold directly, not in a simulation, but in the light of a real and distant world. Findings like these are reshaping what we thought we understood about hot Jupiters everywhere. What we learn from this one planet does not stay with it. The techniques Webb sharpened on WASP-121b, the way it reads chemistry from starlight, the way it separates day from night in an object too far to ever visit, these are tools we can turn on thousands of other worlds. Every strange planet teaches us how to read the next one more clearly. There is no shortage of worlds waiting to be read. Astronomers have now confirmed more than 5,000 exoplanets, a catalog that grows almost faster than we can study it. As of 2024, the tally passed 5,500 confirmed worlds discovered across missions from Kepler to TESS, with thousands more candidates still awaiting confirmation. Most remain little more than dots and dips in starlight. But Webb is pioneering the detailed study of their atmospheres, turning distant points of light into places with weather, with chemistry, with stories of their own. That shift from points of light to places is why a world of stone clouds matters so much. On WASP-121b, rock exists as vapor, as liquid, and as solid, all at once, in different regions of the same planet. It refuses to sit in any single state we find comfortable. It forces us to admit how narrow our earthbound intuition really is, and how much stranger the universe becomes the closer we look. The closer we look, the more that intuition has to bend. This extreme diversity, planets that rain iron and grow clouds of stone, tells us that the worlds we know are only a sliver of what is possible. Webb continues to monitor ultra-hot exoplanets like this one, gathering the data that will decide how far the definition of a planet can truly stretch. And that is the quiet revolution hiding inside this blazing world. WASP-121b does not just add one entry to a list. It expands the boundary of what nature is allowed to build, and it does so in plain view. WHEHE-SKY rains stone, a gas giant that boils its own rock into clouds, tears water apart and reassembles it, and bleeds into space while it burns, is not a curiosity. It is a lesson in humility, proof that the cosmos is stranger and richer than our home planet ever prepared us to imagine. Webb has given us a front row seat to a world remaking the rules of what weather and rock and rain can be. If worlds like this leave you a little more curious about the sky, consider subscribing so you can travel to the next one with us.